In this video, we look at work again by examining the amount of work it takes to lift liquid out of a container. In other words, how much work is done in pumping some liquid out of some container, whether it's water, gasoline, or some other liquid. Now, most textbooks don't get into the following issue, but we're going to have to assume that the pipe we use to pump the liquid out of the container is actually floating on the surface of the liquid, or that it can extend down into the water and not be a fixed length pipe. In other words, it can go to different lengths based on where you want to pump the liquid out from. Consequently, the liquid is sucked out and pumped different distances to get it out of the container. If, on the other hand, your pipe extends to the bottom, then you're always pumping water from the bottom of the container out of the container, and the distance traveled by every layer of water is the same, since it would be pumped from the bottom to the top. In our examples and in our problems, we will instead assume that the pipe itself can be lowered or heightened depending on where the water layer is that we wish to move. The longer the distance we have to move the liquid, the more work is required. When you're looking at a tank, such as this tank of water here, or this tank of water here, again, if you're moving the water layer from right here, it's going to require less work since you're moving it this distance to get out of the container, and then this height to get to the top of the pipe. On the other hand, if the water is down here and you wish to move the water which is at this level, then you're going to have to move the water this height to get out of the vat, which is a farther distance, and then the same distance to get out the outlet pipe. These distances will affect the amount of work that's required, and the work that's done will also depend on the size and shape of the tank, because this will affect the volume of water that is being pumped out. We'll use slices to make our job easier. In this particular case, we'll slice the liquid, say water or gasoline, into very, very thin slices parallel to the bottom of the container and parallel to the surface of the liquid. We're going to start our examples with a circular cylindrical tank, since they're relatively straightforward and easy to think about. When you have a circular cylindrical tank, the bottom of the container and the top of the container are both circles of the same radius, in this example, radius 4. When we say we're going to slice the water, we mean that we're slicing the water into vertical slices by slicing across it horizontally. Now imagine a lot of those layers all stacked up, like in this toy that you see here. Where you see each of the layers that are stacked one upon each other, you can think of these as water layers, almost like stacking plates. All of these water layers make up the volume of water that's in the container. Now, while incredibly flat, the layers are not actually two-dimensional. There is a depth of water in each little slice, which is the differential. You can set the differential to either be dy, meaning it's a vertical slice, or dx. It doesn't matter as long as you're consistent. The text likes to put the origin at the top of the tank, but I think it makes more sense from a physics point of view to put the origin at the bottom of the container and at the bottom of the layers of the liquid. However, it can be done in either way. In this picture here, you can see that I've placed the origin at the bottom of the container in the center, where the center of the circular bottom would be. The water layer's depth can be referred to, as we said, as either dx or dy, depending on whether you want to call the vertical axis the x-axis or the y-axis. I typically tend to call it dy, since I associate it with the y-axis. If we make each depth of water layer thin enough, then the gravitational force on that water layer should be roughly the same all the way through, and the distance that the water in that layer has to be pumped out should be roughly the same. In other words, if you make the water layer thin enough, then you can think of the gravitational force on the top of the water layer and the bottom of the water layer being roughly the same, And the distance that the top water layer and the bottom of the water layer move is also roughly the same. In that sense, then, we can talk about the work done to move a single layer of water or liquid out of the container by pumping it using a floating outlet pipe. Let's go over our formulas again. Remember that work is equal to force applied through a distance. No distance moved, then no work is done. In this case, force can be thought of as mass times acceleration, where our acceleration is due to gravity. What's fighting the water or the liquid moving out of the container is gravity. Mass can be measured by the density times the unit measure, length, area, or volume. In the case of a liquid moving out of a container, we're talking about mass density being a unit with volume. Since our water layer is 3D and it has volume, we can find the volume of the circular disk by taking the area of the base, pi r squared, and multiplying by the depth of the water layer, similar to what we did in volumes of revolution by disks. This gives us pi r squared dx as the volume of a single layer of water, since it's in the circular cylindrical tank. Now we can think about the mass of it as being the density times the volume. The mass of a single water layer is the density times the volume of the single layer of water, which is pi r squared dx. Liquids generally are considered to have constant density, but different liquids will have different densities. Gasoline is less dense than water, and that's why it floats on the surface. Let's now represent the gravitational force on each single layer of water like one single stacking plate. The force on a single layer of water or liquid is equal to mass times acceleration, and since our acceleration is due to gravity, it's mass times gravity. But we saw previously that the mass is given by rho times the volume. Rho times volume gives mass, and mass times gravity gives us force. Therefore, we can represent the volume with pi r squared dx to get the force on a single layer of liquid as rho pi r squared times gravity dx. While the dx is technically part of the volume, it is habitual to put it at the back of the formula where the differential typically goes. So the work done to move that single layer of water a distance of d is given by this formula. F times d, which is equal to mass times acceleration times the distance, which is mass times gravity times distance, but mass is rho times volume times gravity times distance, but volume is pi r squared dx. This makes the work done to move a single layer rho pi r squared gravity distance moved dx. Now we need to talk about the distance that the layer is actually moving. Let's take a look at this picture here. This pictures a right circular cylinder with a single layer of water on the inside. We have a floating outlet pipe, which is right here, which is going to pump just that layer of water at its current height out of the outlet pipe, which is located at the top of the vat. There is a certain distance that the water layer has to be pumped out, which is seen here in the blue arrow. However, the water layer already has a height. If you measure the origin at the bottom of the container and you call the vertical axis the x-axis, then it's already sitting at height x. If our entire vat is 10 meters tall, then the distance that it has to move is not 10 meters, but the full 10 meters minus the x, which represents its current height. In other words, it needs to move 10 meters minus x. You know what's coming next. We're going to add up all the work done on all the individual water layers, take the limit as the depth of each layer goes to 0, and the number of water layers goes to infinity, and take the limit. This will give us a definite integral. I've written the formula here in words to help you to set up the equations. The work done to move water or some other liquid in a right cylindrical tank is the definite integral from the lowest water layer to be moved to the highest water layer to be moved. Notice that the limits of integration refer to where the water is that's being moved. You cannot move water you do not have. And then we have the formula, rho, which is density, times volume, pi r squared dx, gives us mass. Mass times gravity gives us force. And the force is applied through the distance, 10 meters, total height of the vat, minus x, the current height of our water layer. Circular cylinders are easy because the radius of a circular cylinder is always the same value. In other words, it's a constant. The density of the liquid is also going to be a constant, and so is gravity. That makes this integration pretty easy, but the setup of it is not. We won't always be using right circular cylindrical tanks, so we need a more general formula. We're going to let A of x represent the cross-sectional area of the water slice. This will depend on the shape of the tank. It could be rectangular, it could be circular, as in the circular cylinder, or it could be triangular or some other shape. You could use the variable y instead of x if you want to make the vertical axis be the y. We'll let d of x represent the expression for how far each liquid slice has to be moved to get out of where it currently is to the outlet pipe. This will depend only on the height of the outlet pipe and the current height of the water layer. Realize that some outlet pipes, as in the original picture, extend above the height of the container. The current height of the water also affects how far it has to move. The density could vary with the liquid, but the density of the given liquid will not vary within the same problem. Gravity will always be 9.8 meters per second squared for us. We can now write the formula in a more general way. The work done to pump the liquid out of a tank is the definite integral from the lowest level of liquid to be moved to the highest level of liquid to be moved. For example, suppose that you had a container that only had 5 meters of liquid in it, even though the container was 15 meters deep. You cannot move more than the 5 meters of liquid you have, so at most you would be moving from 0 meters to 5 meters. Then the formula becomes rho times the cross-sectional area times the differential dx. Rho times area times dx is rho times volume, which gives mass. Mass times gravity gives us the force, and the force applied through the distance dx gives us the work done. This is what the formula would look like if you choose to let y be the vertical axis instead. We'll assume that gravity is a positive 9.8 meters per second squared, though a physicist would probably make it negative. We're now ready to look at example number 5. In example 5, we want to find the work done to pump the top 3 meters of water from a right circular cylindrical tank that contains 8 meters of water. The outlet pipe is situated 2 meters above the top edge of the tank, which is 10 meters tall and has a radius of 4 meters. Your first job is to draw a picture and label everything that you can from the information in the problem. Don't forget to add the vertical axis in the origin so you can measure the heights. We have a cylindrical tank here and another cylindrical tank here with a single layer of water labeled. Note that our tank is 10 meters tall. Note that the outlet pipe extends 2 meters above the top edge of the tank, which means that it is 12 meters from the bottom of the tank. The radius of the cylindrical container is 4 meters, but there is only water from 0 meters up to 8 meters. The cross-sectional area is pi r squared. Because our radius is a constant 4 meters, this gives us 16 square meters times pi, and it looks like we're missing the square on our meters. and it should definitely be there. We also have the layer of water being delta X or dx deep. The height of our current water layer is X meters tall. I've placed the origin at the center of the container on the bottom. Our vertical axis is going straight up through the container. What is the distance that each water layer gets moved? If I have this water layer here, it has to move up to the top of the tank and then another 2 meters to get out. Since the outlet pipe is 12 meters above the ground of the container, but the current height of the water layer is X, then it will be moved 12 minus X meters. What are the limits of integration? The limits of integration refer to the water that's actually to be moved. Let's look back at the problem statement. Find the work done to pump the top 3 meters of water from a right circular cylindrical tank that contains 8 meters of water. Since we're only pumping out the top 3 meters, that means that we're only moving out this water here from 5 meters up to 8 meters. That's the water that's being moved. The lowest water layer that's to be moved is the 5 meter high, and the top layer to be moved is the one at the very top at 8 meters. These give us our limits of integration. Note that gravity is 9.8 meters per second squared, and water will use a density of 1,000 kilograms per cubic meter. Here's the integral for the setup of this problem. We have the definite integral from 5 meters, the lowest water layer to be moved, to x equal 8 meters, the highest layer of water to be moved. Then we multiply rho times the volume. Rho is the density. Pi r squared dx is the volume of a single layer of water. Then the mass given by rho times volume times gravity gives us the force. The force is applied through the distance, 12 meters minus x. Notice that what we have here is rho times volume to give mass, gravity to be acceleration, so that rho times gravity times pi r squared dx becomes our force. The distance that each water layer moves is 12 meters minus its current height. Take a moment now to pause the video to work out the algebra and the calculus, then turn the video back on to compare your answer to mine. Note that rho, g, and the radius and pi are all constants. Because of that, they can be pulled out of the definite integral from the very beginning, and we don't need to plug in their values until we're ready to calculate actual numbers. That means after the integration has been done. You'll see here that I did substitute in the actual values when the integration was complete. Make sure that you do not round off any values until the final calculation is done. Chances are, once you reach that point, you'll have little to round off. You can leave pi in your answer. This is approximately 2,587,200 pi joules of work to move out the top 3 layers of water from that container. Let's take a look now at example 6, which is a different type of problem because the container is different. In example 6, we need to find the work needed to pump all the water out of a conical tank if the outlet pipe is located at the top edge of the tank, which is 15 feet tall. The water is at a depth of 10 feet initially, and the top of the tank has a radius of 10 feet. A conical tank is shaped like a cone. Our first step is to draw a picture and label everything. Don't forget to label the vertical axis and the origin so you can measure the heights. This is basically what the conical tank looks like. Notice that the conical tank is 15 feet tall and the water is currently at a height of h. Obviously, this picture is not to scale. The radius of the cone is also 10 feet. We're going to set our origin to be at the center of the bottom, which would be here, and we're going to let this be the x-axis moving up. We can approximate the water layers still using right circular cylindrical water layers, but the problem is that the radius of each water layer gets smaller as the water level drops. The radius of the cross-sectional area, in other words, is not a constant. Let's take a look at another picture which shows one of these cylindrical water layers. In this picture, you can see here that we have a cylindrical water layer which is lower down in the water than the one that is here at a height of 10 feet. Notice, too, that the radius at 10 feet is larger than the radius further down. This is generally true as you drop in a cone, that the radius of the water layer decreases. In order to solve this, we will need to use similar triangles from geometry to find an expression for the radius of each water layer in terms of the height x of that individual water layer. The similar triangles can be seen here in the pictures to the right. Notice that our overall tank is 15 feet tall and has a radius of 10 feet. This gives us a triangle which can be outlined here in yellow. Then we can take that triangle and compare it to the triangle we get when taking one of the smaller water layer heights with its radius. Let's take a look at that now. If we take a look at the one that's here at 10 feet, we would essentially be getting this triangle that's here. If we wanted the one lower down, it would give us an even smaller triangle there. Looking at the triangles on the right-hand side, we can see that they both share this angle at the bottom where the tip of the cone is forming an angle. They also have a right angle at the top. And since two of the three angles are the same, the third angle must be the same. That makes these similar triangles. Because they're similar triangles, we know that the proportion of their sides are proportional. In other words, 10 feet to 15 feet must be the same as R1 to H1, and 10 feet to 15 feet must be the same as R2 to H2. Let's take a look now at how to represent this. Using similar triangles, we can write that R1 over H1 has to be equal to the radius of the large triangle of the entire container over the height of the entire container. This allows us to solve for R1 as 2/3 of H1, since the feet both cancel, and 10/15 is equal to 2/3. Since H1 is the height of that particular layer of water, it's its value of x. We can now find the cross-sectional area of the water layer as pi r squared, where r is 2/3 of x. This gives us the volume as pi times quantity 2/3 of x squared dx. Since we're moving all the water, the bottom layer of water is at 0 feet, which is the tip of the cone, and the top layer of water is at 10 feet, which is the depth of the water. Don't move water you don't have by extending the limits of integration to 15 feet. When you look back at the picture, there is no water here in the upper 5 feet, so the limits of integration cannot extend into empty space. How about the distance each layer of water moves? Each layer of water must move out of the floating pipe to the edge of the outlet pipe, which is located at the top edge of the container, 15 feet from the bottom. This water layer has to move further than the one above it. Notice that in each case, it moves 15 feet minus its current height, which is either H1 or H2 or x, as the case may be. The distance then that each water layer moves is the height of the outlet pipe minus the height of the layer, or 15 feet minus x. We have one more problem here, and that is this problem is in the English system. We don't have the density of water in the English system because we don't use mass in the English system. In the English system, we use what's called the weight density of water of 62.4 pounds per cubic foot. This is a measure of gravity on the density of the water. That is, it's a combination of mass and gravity already. 62 pounds per cubic foot is rho g. Let's now set up our problem. We integrate from the lowest layer of water at 0 feet to the top layer of water at 10 feet. This is the water we have to move. Then we have rho gravity times the volume, pi r squared dx, times the distance moved by each water layer. Remember that rho times pi r squared dx is volume, and rho times volume gives mass. Since the density and the gravity and pi are all constants, they can come outside of the fraction and outside the integral. Notice that the x cannot come outside since it is the variable that the differential depends upon. The x squared and the 15 minus x both depend on x and must remain in the integrand. Distribute the x squared and then do the integration. You may wish to pause the video here, work out the algebra and the calculus, then turn the video back on to see if your answer matches mine. Once you have completed the integration, you should have this expression here. Evaluating it at 0 to 10 feet is the part in green. Finally, we substitute the weight density of water, which is rho g combined. That's 62.4 pounds per cubic foot. This gives us 208,000 pi divided by 3 foot-pounds of work required. Let's now look at example number 7. Example 7 is a more difficult problem because the shape is more difficult. We wish to set up the integral to find the work done to pump all the water in a horse trough out of the horse trough. The outlet pipe is located on the top edge of the trough, and the water is initially at a depth of 2 meters in the trough. The trough itself is 4 meters wide, 6 meters long, and 3 meters deep, which means that the water does not fill the trough to begin with. The trough is shaped like an isosceles triangle on the ends. First, we draw a picture and label everything. We can see that the width of the trough is 4 meters by 6 meters long. The trough is 3 meters high, and the end of it looks like an isosceles triangle. Notice that the water only reaches a depth of 2 meters from the beginning. When you're looking straight down from above, the surface of the water looks like a rectangle. As the water level drops, however, while it's always 6 meters long, the width of it changes. In fact, our width does not start at 4 meters because the ends are shaped like isosceles triangles. We need to come up with a way of expressing the area of that layer of water. In other words, we need to know what the width of each layer of water is. The width will have to be given in terms of the other measures that are available in the problem. While each layer of water is super thin, it's still a box. As the water level drops, the width of these boxes decreases. The length will stay 6 feet because that's the length of the trough, and we can assume that the depth of the water layers stays the same at dx. Remember, we'll allow dx to go to 0. We need an expression for the width in terms of the differential variable, which is x. If we knew what the width was, we could multiply the length times the width times the differential dx to get the volume of each slice of water. Let's now look at the end of the trough, the isosceles triangle. We're going to need similar triangles again. Notice that our original width of the entire trough is 4 meters, and because it is isosceles, that means that half of the width of the trough is 2 meters. We can divide the end of the trough into two right triangles that you see here. The width of each layer of water is double the pink that you see here on each side. I've labeled one of the sides W sub I, and the actual width is 2W sub I, since it goes on both sides. We know that the height of the water layer is at X sub I, and we know that we can write an equation for the overall trough of half the width being 2 meters and the height being 3 meters. Then we can compare with similar triangles W sub I to its height X sub I. Using similar triangles, we can set up the proportion W sub I divided by its height X sub I is equal to half the width of the original trough divided by its height, 3 meters. The meters will cancel, and we can move the X sub I to the right to get W sub I is equal to 2/3 of X sub I. Since our W sub I was really only half of the width of the water layer, we'll need to double it to get the true width, which is 4/3 X sub I. Let's now organize our information to set up the integral. Water goes from 0 meters to 2 meters, so our integral should go from 0 meters to 2 meters. The cross-sectional area of the rectangular box for our water slice layer is going to be 6 meters long, 4/3 X meters wide, and dx meters high. That gives us the volume. The distance that the water layer gets pumped out of the container depends on where the outlet pipe is. In our case, the outlet pipe is located here at the top of the container. That means that the distance that it travels is 3 meters minus its current height of x. Setting up our equation, we have rho times volume, and our volume is given by 6 meters times 4/3 x times dx. 6 meters times 4/3 x dx gives us instead 8x dx. Multiplying rho by the volume gives us the mass. Mass times gravity gives us the force. The force is applied through the distance, 3 meters minus x. Go ahead and pause the video, work out the algebra and the calculus, then turn the video on to compare your answer to mine. When you're done, you should have 261,333 1/3 joules of work to move the water out of the trough. We are going to skip the hydrostatic force and pressure section, but you're welcome to read it if you want to find out about pressure on a dam and how the pressure increases as you move lower in the water due to the weight of the water above it. This will be the end of this video and the end of our section on work.